One way to acquire an electrostatic charge is to come in close contact with another object that consists of different material. Cotton, for example, has greater attraction for electrons than wool. Therefore, when these materials come in close contact with each other, electrons transfer from wool to cotton. The cotton now has an overall negative charge, and the wool an overall positive charge. Their opposite charges account for the static cling when you attempt to separate them. The easiest way to neutralize a charged object is to connect it to the Earth with a good conductor called a ground. If the object is negatively charged, the excess electrons flow into the ground until it is neutral. If it is positively charged, electrons flow from the ground into the object until once again it is neutralized. Close contact between two neutral objects is not the only way to acquire an electrostatic charge. If a neutral object is touched by a charged one, there will be a transfer of charge as electrons flow from the charged object to the neutral one. And how do we detect charge? A metal leaf electroscope can be used to detect relatively small quantities of charge. When it's touched by a positively charged rod, electrons move from the electroscope onto the rod, leaving an excess of positive charge. As a result, the metal leaves repel each other, evidence that the electroscope is charged. Have you ever noticed that an electroscope, when approached by a charged rod, seems to anticipate what is about to happen? The leaves diverge even though the rod does not make contact. If the rod is removed, the leaves collapse again. What's going on here? Well, let's apply some of the theory we've learned so far. We can visualize the electrical condition of the rod and the electroscope by showing a representative sample of the charges. Since the electroscope is metal, electrons can move with relative ease within it. If, as a result of their random motion, some electrons come close to each other, the repulsive forces that they exert on each other ensure that they will very quickly move apart again. When a positively charged rod moves towards the knob, the charges interact. The electrons in the electroscope will try to move towards the rod. And as they do so, will flow out of the metal leaves, making the leaves positive. As a result, the leaves repel each other and diverge. When the electrons in the electroscope move towards the rod, they get closer to each other and repel each other more strongly. So, for each electron on the knob, the attractive force of the positively charged rod is balanced, both by the repulsive force of the other electrons near it and the attraction of the positively charged leaves. If we look at the electroscope as a whole, we find that the top is negatively charged and the bottom is positively charged. Since no charge has been transferred, the electroscope as a whole is still neutral. It has, however, experienced induced charge separation. If the positively charged rod is removed, the electrons will no longer remain concentrated in the knob, but spread out uniformly throughout the electroscope. As a result, the electroscope no longer has induced separation. Let's bring the rod close to the electroscope again. This time we'll ground the electroscope while the positively charged rod is held nearby. Remember that the electrons in the electroscope are attracted by the positive charge on the rod. The positively charged leaves are also attracting electrons. The ground allows electrons to enter from the Earth. As a result, the leaves of the electroscope become neutral and collapse. If we remove the ground and then the rod, look what happens. The repulsion of the excess electrons will cause them to move as far away from each other as possible. The leaves, which are now negatively charged, diverge. Because electrons entered the electroscope when it was grounded, it now has an overall negative charge. Surprised? We succeeded in charging an electroscope negatively using a positively charged rod and a ground. Watch this sequence. Did you notice that throughout the entire sequence, there was no exchange of charge between the rod and the electroscope? We call this process charging by induction. It occurs when a charged object is used to charge a neutral one without discharging itself. Since there was no exchange of charge between the rod and the electroscope, the rod can be used to charge any number of electroscopes. Each electroscope will acquire a charge opposite to that of the rod. Charging by induction often occurs in nature. Thunderclouds frequently have a strong negative charge, which repels the electrons in the Earth below. The result is an induced positive charge on the ground immediately beneath the cloud. If the charge difference between the cloud and the ground becomes great enough, a massive flow of charge results. Some people actually call it lightning and thunder. Benjamin Franklin was the first to demonstrate that lightning is an electrical discharge. He flew a kite. When he attached a key to the kite string, the sparks that jumped from the key to his hand showed that the clouds carried an electrical charge that was being conducted by the kite string.
You really think so? Of course.
In the next program, we will investigate this flow of charge.